as usual, just 2 or 3 words from my side as a short introduction. Then we're going to start with Kritika's talk, and she's going to talk about PyTorch Opacus, and which is deep learning with differential privacy. Kritika is currently a research scientist at OpenMind, and I also read from her Twitter stream recently that she's quite successful in terms of publishing, having a NeurIPS workshop publication this year. So congratulations definitely to that. And we look really much forward to your talk. For those of you who have joined us previously, you know that we typically collect questions from the audience, and we use a tool called Slido for this. So we will share Slido, the link to Slido in a minute, and we will also share it in the chat so that you can already start collecting questions and voting for questions during the talk. But we will also give you 5 minutes after the talk so that we can collect more questions, vote on questions, and then we will have roughly 15 minutes where we will go through the most upvoted questions together with Kritika so that she can answer to your individual questions. And in case 15 minutes are not sufficient, we are going to have a networking session after the Q&A where we are going to use the tool called Wanda, which was previously called YoTribe. You should already have received links, passcodes, and all those kind of things in the email from meetup.com, but in case you missed it or didn't receive it, we will share it here as well. And yeah, just like I said, here's already the QR code for Slido for collecting the questions. Event code is pretty straightforward, so it's CAIML15. So if you just go to Slido, you can just enter our event code and you will be directed to the correct Slido event. Besides that, there's also the link that we're going to share in the chat. Yeah, that's pretty much from my side. Just before we start with Kritika's talk, just one small ask to the audience. If you enjoy the event, we would really appreciate if you share it on Twitter, LinkedIn, or whatever social media form you're using, because this just helps us to get also a bigger audience and to attract more attendees and speakers for future events. So thank you very much already in advance. We really appreciate your help on this side. And now I would say enjoy the rest of the evening, and I would hand over to Kritika for her talk on PyTorch Opacus. Thanks.
Okay. Hello, everyone. I hope I'm audible.
Yes.
Yes.
Works perfect.
Okay. So I am really grateful to be here today, and I'm quite excited to talk about PyTorch Opacus and differential privacy in general. And thank you for coming. So I'll get started with the presentation. Is my screen visible to everyone?
Yes, we can see your screen.
All right. So today's talk is on PyTorch Opacus, which is a library that gives us the ability to make deep learning differentially private. And I'm going to start by telling you all a little bit about myself. I'm a master's student at the Machine Learning Lab in IIIT Hyderabad, which is in India. And I am a part of an open source organization called OpenMind, where I lead the efforts in differential privacy research and development. Generally, my work is around deep learning and differential privacy and game theory. So a little more about OpenMind, because a lot of this work has been possible because of my contributions to OpenMind. So OpenMind is a community which is lowering the barrier to entry to secure and private AI technologies, which enables us to get access to more and more data in very sensitive domains such as healthcare. So recently, they have received huge sums of funding from organizations like PyTorch and Oxford and It's a growing community of 10,000 people almost at this point, and I would encourage everybody else who is looking for good opportunities, not just in open source contribution as a developer, but also as a researcher, to consider Open Mind. Yeah. So the brief agenda of today's talk is first, we're going to be talking about differential privacy, followed by differential privacy in deep learning. Then we talk specifically about the PyTorch Opacus library, how it's used, and followed by your Q&A. So now I'll start with a fun question. I understand that this crowd is very international and this question probably does not apply to a lot of people, but just imagine yourself to be American for a minute and think if you would vote for Trump or not in the elections. So such a question might be controversial. Maybe you reveal your political preferences to people. But when we try to take a survey about such sensitive questions and sensitive data, we still want the statistics to truly represent what the people think. And so how do we ask such questions, which could be private or sensitive to people? So we're going to do a small exercise. If you would have voted for Trump in the elections or not, I'll ask you to pick a random integer. Now, in case that the random number that you picked is an odd number, you're going to answer truthfully in the survey. And in the case that the random number you picked is even, I'm going to ask you to pick another random number. So now the second random number that you picked, if that is an odd number, you're going to answer yes. Otherwise, you're going to answer no. So this simple mechanism, what this mechanism gives you, just facing a lot of disturbance. Someone's can everyone?
Maybe somebody's not muted. Can everybody please mute themselves?
Jose De Silva. Yeah, perfect. I think it's good now.
Yeah. So I'll continue now. So what this simple mechanism gives to the people participating in the survey is the power of deniability. In the case that they answered yes in the survey, nobody can tell whether you actually voted for Trump or whether this simple game made you say yes in the survey. So this method, which is pretty old, is known as randomized response or plausible deniability. And so what this does for us is that it still protects the ratio of the actual answers that you're going to get over a large crowd. So if 45% of the people actually voted for Trump, that is what is going to show up in the end. Despite that half the time people are going to be answering randomly. So differential privacy is a very recent research field, which it's a very recent development. It's just been for around 15 years or so, and it builds on this simple intuition. So, yeah. So differential privacy, it comes from the field of cryptography. It's a system for publicly sharing meaningful information about data that could be private or sensitive. And the way it does so is that it masks any single person's contributions, but at the same time, the bigger picture remains the same. And the way it does that is by randomly adding noise to the entire data set. So the key advantages of differential privacy is that it's the strongest mathematical guarantee of privacy that we have. It doesn't require any sort of modeling of our adversary and what kind of attacks that adversary can perform. So it's like assuming the worst case adversary, like the adversary has knowledge of the entire world, everything in it, except the specific data that we're trying to produce, to protect. And another beautiful thing about differential privacy is that you can query your system multiple times, and that guarantee, that mathematical guarantee, it composes, or it adds up very naturally. And it's something that gives us a quantifiable measure of privacy, which is quite unique. So I'm just going to start off with a simple example to give a clearer intuition. Consider this simple data set of how many people are visiting a restaurant at a certain time of the day. So as you can see, this indicates that 10 people visited at 3 p.m. and so on, and nobody visited at 1 a.m. But if after some time, somebody actually does visit at 1 a.m., then what happens is that it's easy for an adversary to figure out who that one person is based on other observations. So such class of attacks are known as linkage attacks, where you use external data and link it to very fine differences that you notice in statistics of your original data set to find out more about who is in the original data set. So this example shows why we need to protect our data, even the statistics of our data, even though it might seem like this is not giving away anyone's personal identity or compromising anyone's privacy. So what differential privacy does is it's going to sample noise from a distribution. Maybe it could be the Gaussian distribution of a specific mean and variance values. And once this noise is added to the data, it's going to look something like this. It's going to be different from the original data, but it's still going to preserve the overall shape or the overall bigger picture of what we're trying to learn, usually in data science or machine learning. So how would we go about doing something like this? Just a simple code to show what it's going to be like. Say your original data is this array, and the sensitivity of the data, how sensitive it is to change, is 1, because by the increase of one person, the visitor count increases only by 1. So that is known as the sensitivity of this data. We define something called a privacy budget, which is a value called epsilon. And that and the sensitivity, delta F, these two things will directly impact what the variance of our noise distribution is going to be like. So this epsilon is the privacy budget that we decide. Del F is the sensitivity, and these two factors together help us determine the variance of the noise distribution. So as you can see, it's directly proportional to how sensitive the data set is, and it's inversely proportional to the privacy budget that we choose. And with some basic calculations, we get the mean and the variance of the Gaussian distribution. And then we sample random noise from this Gaussian distribution, and we simply add that random noise to the original data. And so if you look at this plot, you will see that the original data is the orange line and the noisy data is the blue line. In this case, the parameters we chose were large enough to create a huge distortion from the original curve, which means that our noisy data is highly private. And since the variance of the data set is inversely proportional to the privacy budget epsilon, the smaller the budget, the more privacy you're going to achieve, and the noisier your result is going to be. So more formally, differential privacy says that for any two databases that differ in only one single person's data point, and for any possible output on that query or that algorithm M, that algorithm or query is said to be differentially private. It's said to be epsilon differentially private if the probability of these two outputs being exactly the same is upper bounded by e to the power epsilon. So the ratio of the probabilities of these two outputs, that is applying the algorithm on D and applying the algorithm on dataset D prime, if they give the same output, if that probability ratio is bounded by e to the power epsilon, where epsilon is a small positive value, that is the differential privacy guarantee that you get. And this is how epsilon is the way we are able to quantify the level of privacy that we achieve. So, and the way we do this is we have, as we saw in the simple example, we need a way to add random noise to the data. And the key factors for deciding how to do that is step one, you pick a noise distribution. So what kind of noise distribution are you going to pick? It could be coming from Laplacian distribution, it could be a Gaussian distribution, it could be multiple others. And now what parameters are you going to choose as the mean and the variance of such distributions? That comes from the privacy budget epsilon that we choose and the sensitivity of the query that we choose. So in the previous example, you saw that the query was a simple one. It was just counting the number of visitors. And the sensitivity of such a query is 1. But if you consider different queries, such as the sum of all the ages of the people who came in, then that is going to be that's going to have a much larger sensitivity. Maybe the oldest person who entered that restaurant was 50 years old. So then in that case, the sensitivity of that query becomes 50 because that's how much your final sum value can change based on that person being in the data set or not. So generally, differential privacy works well with queries that have low sensitivity. Okay, I'm going to pause here and I'm going to see if anybody has any questions up till now, and once we clarify that, we can move forward. If anybody has any questions, they can just unmute themselves and ask. Okay, so Nate has a question. What would go into choosing epsilon and what would be a typical value? That's a great question. So epsilon is one of those parameters where you have to perform a lot of trial and error to understand what epsilon is good for your application. The rule of thumb is the smaller the epsilon, the better, because it gives you more privacy. But if it's too small, then you are going to lose out a lot on the accuracy of the result that you're trying to get. So one simple guide to see what epsilon is initially the randomized response that I had shown that was discussing plausible deniability in the case of who voted for Trump. The epsilon of that mechanism is a natural log of 3, and that turns out to be 1.09. So generally, people start with 1.09 as your base epsilon, and they tweak it from there, so that you always have a 50% say that this person was in the data set or not. So that's where people usually start with. I hope that clears your doubt. And any other questions? Okay, I'm going to continue. So this section is applying differential privacy to deep learning. So I'm sure most of you have a decent background in what deep learning does, what it's trying to achieve, and I'm going to just talk about it briefly. And so in deep learning, we start with a group of people who have been, whose data we have collected in some form, and these people are the source of data, and their privacy is the privacy that we're trying to preserve at the end of the day. So this data that we get from the people is going to go through a whole neural network recipe, which will consist of your model, an optimizer, a loss function, and many other fine things which go into really creating a good neural network. So there are lots of variables in this situation where you can think of what the architecture of your model should be, of course, the weights that you're going to learn, what loss function you're going to choose, how you're going to optimize on that loss function, and so on. And the key rule, the key thing in neural networks and deep learning is that we want a model that is going to get a high accuracy because it generalizes well on the data, not because it memorizes the data. And that intuition really matches with the intuition of differential privacy, where we want people to still get an idea of the bigger picture, but can't look at any single individual's contributions. So the key question is, where do we add noise in this entire process? We could add noise to the input data, but usually the problem with that is the earlier your stage of adding noise, the more noise that you have to add. So it's if you want to publicly release that data set, you're going to add a lot of noise to it before publicly releasing it to maintain its privacy. But another thing that you can do is you can finally release a trained model and make that model noisy and private. So you're going to have to add much lesser noise to get the same privacy guarantee as your previous case. So we're going to see how to pick this. So just a quick understanding of the mini batch stochastic gradient descent optimizer, just to get a decent idea of what the pipeline looks like. We have a huge data set. We divide it into mini batches of some size. Often people choose it to be 32 or 64 or 128. And so in this example, you can see that your mini batch size is 4. What's going to happen is this data is going to be sent to the first layer of your network, and it's going to be multiplied and operated with the parameters of the model corresponding to the first layer. This weighted sum is going to go ahead further to the next layer and so on. And finally, the predictions that you make will be used to calculate the loss value, that how off are your predictions from the true labels or the true values. This is what the forward pass looks like. And now we're going to look at the backward pass of mini batch stochastic gradient descent. We'll start from the loss function, propagate the loss gradients backwards across each layer, and then that's what's going to update the parameters. So this is your normal stochastic gradient descent optimizer. And now we're going to look at a differentially private version of this stochastic gradient descent optimizer. So it's going to start the same way. You propagate your loss gradients to each of the layers. But before you update the parameters, you're going to clip the gradients. So what's happening is that your gradients could be really large in value, and in an absolute sense, they could be really large in value, which means that it's going to show that some people's contribution is really large and it's making the data more sensitive. So to keep the sensitivity under control, what we do is we clip the gradient values to a defined limit so that we can control the sensitivity of the data. And after clipping the gradients, we're going to aggregate these clipped gradients or average them. And once we have this aggregated clipped gradients, we're going to be adding Gaussian noise or Laplacian noise based on whatever distribution we pick. And after that, these noisy averaged clipped gradients are what are going to go and update the parameters of the model. So this is what the backward pass of differentially private stochastic gradient descent looks like. And this is what all the deep learning with differential privacy libraries are implementing. So now I'm going to talk a little bit about PyTorch Opacus. So to start with, it's a new library. It has recently been made, and it has been a work in progress for a couple years. But recently is where they have gotten the key insight into making it super fast. So if you see in the previous slide, the huge bottleneck here is that before, so this clipping gradients is a single example gradient operation. That means effectively it makes your batch size equal to 1, or it brings you back to normal stochastic gradient descent instead of mini batch. And that makes it really, really slow. So PyTorch Opacus has used some really interesting mathematical techniques with linear algebra, which have made this much, much faster. And yeah, that's the key contribution of Opacus, the key new contribution of Opacus in this subfield. So Opacus is high speed, of course. It's scalable, and the way it has been made, the API, it's really easy to adopt differential privacy in machine learning. It's considered to be cryptographically much more safer than a lot of the other libraries because of the way they have implemented their random algorithms. And yeah, it is interactive in the sense that you can actively monitor what your budget is looking like at every step of training and so on. So as you can see, you can easily find the Opacus library on GitHub. And yeah, you can start contributing there. You can find a lot of documents, examples to really get started. A lot of what I learned was from these resources, and that has helped me a lot. So the API, it's really simple and beautiful. You just need to do a simple pip install Opacus, and anytime you create a model and an optimizer, any optimizer that you use, you can easily just attach what is known as a privacy engine to your optimizer, and that's it. That's all it takes. So a lot of the parameters that you see in the privacy engine, such as alphas and noise multipliers and max grad norm, all of these come from differential privacy. So I'm not going to go into what alphas are, but noise multiplier is just your, it's just an indication of the standard deviation of your distribution. And max grad norm is like the clipping value that we're using to keep the sensitivity under control. So now I'm going to go for a simple MNIST private image classification example. So this example just uses 20 lines of code. It uses the PyTorch Opacus library, of course, and it's on the MNIST dataset. So the MNIST dataset, for those of you who are not familiar, is a huge dataset of handwritten digits, and so finally you just have 10 output classes of the 10 digits, and it's the standard that's used in a lot of machine learning and computer vision research. So so your first step is to import the PyTorch and Opacus libraries and any other simple helper libraries that you will need. The second step is to actually use data loaders to load MNIST data and make the training data set and the test data set. In this, you will see that I have also normalized the data using its mean and standard deviation, and I have specified the batch sizes as well. So now the next step is to create a simple model. Here you can see it's a simple sequential model with various layers, convolutional layers, relative activations, max pooling layers, and so on. And this is usually a creative part. Like you can pick your model architecture and you can experiment there a lot. And the optimizer that we're going for is one of the more basic ones. That's the SGD optimizer without any sort of momentum or anything, and a small learning rate of 0.05. So yeah, this is the key step. We create a privacy engine and we attach this to the optimizer. And the next part is creating a training function. So here you can see that apart from the standard input parameters, you also take in something known as delta. And that delta is just like epsilon. It's another privacy budget, which I'm not going to go into right now, but it's a lot like it's a lot like epsilon. So you can keep that in mind. And the loss chosen is the cross entropy loss. And finally, you can see every time the optimizer takes a step, the second part of the train function, yeah, here. So at the end of every optimizer step, you're getting the budget, the get privacy spent budget via the optimizer's privacy engine. So that gives you the epsilon value that we're looking for. And so for this example, I chose to train it for 10 epochs. And yeah, so the next step is just to observe the training process. And here you see that the loss is gradually decreasing. And in each round, you're able to see how much privacy budget has been spent. And that is obviously increasing gradually. And so in this case, the best loss that we get to is around 0.53. And now we're going to compare it with the training loss that we obtain in the case of non-private learning. So you can see the comparison that in a private training process, you get to about 0.53, but in the non-private case, you get to about 0.01 within the same sort of framework of operation. And the last part is to test what your model, how well your model is doing. And as you see, there is a drop in accuracy from 99 to 92, thanks to the privacy that we introduced. So this is always a trade-off, the amount of privacy that you're able to achieve and how much utility or accuracy you're able to get. And so if you want to play around with this code and try this library out for yourself, one way is to start with this blog, which is just using 20 lines of code. You are able to build a simple network as I just showed it to you. So you can find this in the OpenMind blog. And yeah, now just briefly going to talk about how Opacus performs in relation to other libraries that do the same thing. So recently, very recently, in fact, a group of researchers at the University of Waterloo did this study where they found that so they themselves used JAX to create their own version of deep learning, differentially private deep learning, and their library seemed to be doing the best of all the other comparisons that they made. So for MNIST CNN, you can see that Opacus seems to be doing much better than Privacy, which was the first real library that did this, and TensorFlow Privacy library as well, on all batch sizes except the batch size of 16. Whereas JAX seems to have, their method has a much better result compared to all the other results so far. And that is definitely a very interesting direction to look into. And that's it. That's all I have today. And I hope you all learned something. Happy to take questions now.
Great. Thank you very much, Kritika, for this great presentation. Yeah, then I would suggest that everybody can now add their questions to Slido. I will also share the slide with the link to Slido again, and maybe we're also going to add it to the chat. And then let's meet in roughly 5 minutes again so that we can go through the questions.
Okay, Fabian, should I start taking questions from Slido?
I would suggest that we wait for 5 minutes roughly so that everybody can add their questions and vote. And then we're just going to start with the most upvoted questions in order then.
Sure. There are so many really great questions here.
Yes, definitely. And I mean, I think I'm not sure if we have time for all of them, but then maybe in the networking sessions, you can answer to the other questions. I mean, there's some really in-depth questions that probably will also make a great discussion afterwards.
Absolutely, yeah. Maybe we should start taking questions because I guess there are lots of them.
Yes, agreed. Let me actually share the questions so everybody sees them. 1 second. Okay, then maybe we can actually start with the first question.
Okay. So, are there any regularization benefits to adding noise to the gradients? Absolutely, yes. It has been shown that the positive byproduct of using differential privacy is that it acts as a great regularizer, and it helps to make a more generalizable model. And while there have not been enough in-depth studies in this area, but there's a lot of potential. Yeah. So I'm going to take the next question. How can I contribute to OpenMind and get involved? The easiest way to get involved is to join the Slack channel. So it's a really active community, really friendly community. I can add the link here. It's easy for you to find it. You join the Slack channel, and there will be people who are going to willing to help you out, figure out what exactly you want to do there and how you can contribute and how you can learn as well. So even if you have no background in the secure and private AI space, you are more than welcome to join and learn. So the next question, what are the main differences in the JAX implementation? Does it use the same DP algorithms, but just happens to be faster? So the answer to that is it uses just-in-time compiler and really efficient vectorization of the code. And it does use the same DP algorithm, but it's not that, it's the underlying structure that's different. So the DP algorithm is going to be the same because that is your standard benchmark, but just being more efficient with how you make your backward passes. That's the key place where the JAX implementation is doing really well. So I'll take the next question. Could you maybe again describe a use case where it makes sense to use private differential deep learning models because it comes up with a price tag of low accuracy? So the most simple example for this is consider healthcare data. Maybe you want to work on better prediction of things like cancer and diabetes. So there's a trade-off. It's not easy for any of us to get access to such data because it's highly sensitive and private. The hospitals wouldn't want to release such data because it can be potentially harmful to the people who are contributing to that data set. So that's the cost you pay. You get access to really important and meaningful data sets by making them differentially private. And then even though you're not able to achieve 99% accuracy, maybe you're getting around 95% accuracy, but still it allows you to get access to a lot of data that you originally couldn't. So that's the key trade-off. Okay, next really fascinating question. What does differential privacy mean for the MNIST dataset? And what information about the original dataset is hidden or obfuscated? So MNIST is based on handwritten digits. So maybe so now the key question is, for some adversary, the key question is, was Fabian's handwriting in the data set or not? Was Fabian's handwriting of the digits from 0 to 9, was it in the data set or not? And they can do that by maybe finding Fabian's handwriting elsewhere and somehow creating this very strong correlation with some digits that he finds in the data set. So that's the problem. Just by other external data, by linkage attacks, I can tell whether Fabian's handwriting, whether Fabian's handwritten digits were in the data set or not. So if we make it differentially private, even though someone else has Fabian's handwriting from elsewhere, they will not be able to tell whether he participated in the MNIST data set or not. I hope that helps. So next question. Is OpenMind a good starting point to start learning more about differential privacy? Yeah, absolutely. I think you will find the largest open source community working on differential privacy in OpenMind. Another good place to look at is the OpenDB community, which has been a strong effort by Harvard and Microsoft together. So they are building a lot of libraries and tools for differential privacy. So, but that you will find is much more academic and much more rigorous in some sense. In OpenMind, it's a good starting point, a good entry point into differential privacy. So next question. The epsilon is not a fixed hyperparameter before training, but rather being computed for each iteration. It is not a so what usually happens with epsilon or a privacy budget is you pick a budget for the entire training process. You say that my entire training process should be under a budget of 10.5. And so your training will happen and it will spend some of that epsilon budget, some fraction of it in each training loop. And it will only train until it reaches the privacy budget of 10.5 that you had specified. It won't train any further. So that's how it usually goes. Next thing, thank you for saying that. Next question. So the epsilon, that's been taken care of. Okay. Are there any libraries that will help with assessing privacy after you've trained your model? This is a good library because you have to specify the privacy budget that you want. And of course, there are ways to optimize it. There are some variables which you can use to optimize it. Another good library which helps you be even more interactive with the privacy budget is called AutoDP, and it has been built by some researchers, I think, at Google. So definitely check out AutoDP on GitHub. And next question is, are there any optimization methods that work better with DP? So definitely in the process of training differentially private deep learning models, I remember when I was doing that myself and tweaking the learning rate and the weight decay factor and specifying the different privacy budgets, all of them together definitely helps you achieve better privacy. And epsilon also becomes a hyperparameter in your training process. So yeah, you try it out with all of these things. The learning rate definitely creates a huge impact. Another thing that you will find is that the original DP-SGD paper worked with a ReLU activation, and ReLU is an unbounded activation, so it can range, its values can range anywhere from 0 to infinity. But instead, if you work with bounded activation functions, like the sigmoid class of functions, then you're going to get much better results, because that helps you bound the data automatically, and it reduces the amount of effort the clipping function has to do, essentially. And it doesn't counter, it's like in the original case, the ReLU activation and the clipping function are always at war with each other. But if you use a bounded activation function, they actually go hand in hand. You will find this result in an ICLR paper by Nicholas Papernot. It's called Making the Shoe Fit, and it has a really good comparison of these methods. Okay, next question. What's next for open source differential privacy? Can we expect further gains? Absolutely. So just for open source differential privacy, there is a lot that needs to be done. So it's like it's catching up with the research. It's trying to make the best use of adding differential privacy to maybe contact tracing apps, to medical healthcare AI pipelines, and so on. The in a more research-oriented sense, there is recent work by Apple on individual differential privacy, where you don't work with differential privacy of a data set, but you work with differential privacy budget for each and every individual in the data set. And that is turning out to be an even stronger, but it's more data specific. So it's not data independent guarantee, but it is a stronger guarantee of differential privacy. So yeah, if you are interested in that line, that is definitely something to look into. So the paper is called Individual Differential Privacy, and it's by Vitaly Feldman. So the next question, do you think using generative models which learn underlying distributions and then regenerate it would also be a way for differential privacy? Possibly. So even if you look at the basics behind generative models, it's still learning from the data. So the problem there is, what if it memorizes the data? What if in the process of generating images of faces, I generate an image of a face that's very similar to that of Narendra Modi or Angelina Jolie or anybody specific? So that's the key question there. So yeah, it's like you can make generative models differentially private as well. Or you can design generative models that give it to you for free. And possibly it might not give you the highest accuracy, but it would definitely be a more general generative model. And the last question, if you use dropout during training, does that help or interfere with DP? It's a really interesting question. I'm currently working on some experiments to test that. Of course, the intuition is that dropout is going to help with DP, of course. because it helps you make better generalizations. The only issue with dropout in some sense is that when you use dropout, you also have to rescale the values, which could, and that usually means upscale the values, and that could result in increasing the sensitivity of your function, of your neural network. So yeah, it's a work in progress. And yeah, thank you.
Okay, cool. Yeah, impressive how quickly you were able to run through all of those questions. Really amazing. Thank you very much, not only for this, but also for your great presentation. I think it was a really great presentation and really nice with all the coding examples, and it was really nice to learn more about that topic, which I hadn't too much knowledge about before either. So thank you very much again. So a virtual applause from my side. And I've already now put the last slide here on the screen. Yeah, first thing, we would really appreciate your feedback. As usual, we have a link to a very short SurveyMonkey survey where we just ask 2 or 3 questions so that we can continue to improve our meetup. And the second thing is here on the slides is also, again, the link to Wonder. And we would invite everybody now to join us on Wonder to just have a little bit small talk and maybe have some more Q&A with Kritika and yeah, to do some networking. So thanks you very much again, Kritika, for the talk, and thanks to everybody who joined us tonight. And in case we don't see you in Wonder, then we'll see hopefully next time in the next year. So thank you very much and see you then. Bye.
Thank you, everyone. Yeah, this happened because of all of you. So I'm really grateful.